Automation became the significant word of this era. Possible without intervention of electronics. Good evening, people. This is Meher from Lead Society, and here we are with Let's Talk Live 3.2. The last two editions of Let's Talk Live have been a great success, teaching us the norms of the corporate world and the future in robotics, and the art to ace hackathons. Today, we are here with Ms. Palak Talwar. She has been serving as a senior engineer at Lyft, a value-based company, for the past 4 years. She had given her contribution to FEV North America, an automotive consulting company, as a function safety and powertrain engineer with experience in an embedded control system, function safety, image processing, MATLAB, Simulink, embedded system, control system are her renowned skills. She has completed her MS in control systems from the University of Michigan. Apart from this, she also holds an approved patent on control redundancy. Throughout her career, she has also obtained ISO 26262 certification. Today, she will share some fruitful insights from her 7 years of working experience. Hello, Palak.
Hi,
Welcome to the show.
thank you. Thanks for having me. How are you?
I'm great. How are you? So I won't take much of your time, and the stage is all yours.
All right, thank you. Hi, all. It was really nice, hearing about all the work that I've done in the past. I was meaning to give my introduction, but I think Mehak has already done a great job. So I'll just, dig into the presentation and, let's go from there. All right. So I think to begin with, I was thinking of, again, talking about myself, what I've done and, about my journey. But I guess, if you have any questions in the end to know what sort of interested me to get to control systems and to get to University of Michigan, to get to functional safety, I'm happy to talk about those in the end. But I think even though Meg, already gave my introduction, just quickly, I'll just spend like a minute or two to talk about myself, my journey. I graduated from North Cap University. It was previously called ITM, Institute of Technology and Management. It's in Gurgaon. I did my BS or BE in Electronics and Communication Engineering Bachelor's. From there, I did my master's in Electrical Engineering Systems from University of Michigan. I picked control systems as my master's and signal processing as my minor. There, I'm happy to talk more about the choices later as part of the question, Q&A in the end. From there, I worked as a software developer, software engineer for a consulting company called FEV. It's in North America. I worked there for a couple of years because it was a consulting company. So it had, a lot of exposure. So we had multiple projects going on at the same time. So my focus mainly was, talking about basically mainly working on control systems implementation, testing of those functions, working on functional safety aspects related to control systems, which I'm happy to talk about, as we go through the slides. And then finally, I'm at Lyft. I continued my journey in safety engineering space at Lyft. Um, I started out working as a software safety engineer, but throughout this, 4 years of journey at Lyft, I have experienced, from, something that was not there, in terms of setting up a safety process at an organization to a prototype or a workable model when it comes to developing a self-driving car. So I think with that, let's go on to the next slide. You know, before we go into, talk about these specific safety mechanisms and, what do we mean by safety? How do we implement safety? And why is it important? What key things do we have to think about safety? I just wanted to give a little bit of introduction, like, what is Lyft? You might have obviously heard of Lyft, and just an overview of, autonomy levels, like what are the different levels of autonomy? Um, what are the key benefits and challenges when it comes to developing a self-driving car, right? So with that, what does Lyft do? So the picture that you see here is actually one of the images that was released by Lyft some time back. It's a Ford Fusion hybrid, and it was released probably, I think I would say 2 years ago, 1 to 2 years ago. And you can see that it has like its own suite, sensors and cameras, lidars, radars, and everything at the top. Um, Lyft is a ride-sharing company. It started off as a ride-sharing company, and its main competitor is Uber in US and Canada. In 2017, approximately, it started its own self-driving division, which is called Lyft Level 5. It was mainly focused on building self-driving technology and integrating it into different platforms, not building the car from scratch, but partnering with different OEMs like manufacturers, automotive manufacturing companies, and then integrating self-driving technology on top of it. So it started its journey sometime in 2017, and that's around the same time when I joined Lyft. So it was pretty new. It was literally like a startup, and we had very few people. We didn't have a process in terms of safety. We didn't have a car. We didn't have a platform to begin with. So it was a really nice journey to begin from there, and have a platform to learn about the platform. Whether it was, in this case, it was Ford Fusion, and then to integrate our technology into that platform, right? And also think about safety aspects of it. You obviously know, you have key competitors when it comes to self-driving, and Tesla is one of the, well-known. Simon, one of my good friends, he might have talked about this before in his sessions. Waymo, that is, Google's project, Uber, and a few other startups that are currently working on self-driving technology. Before we go into, again, safety, right? I just wanted to talk a little bit about, like, at very high level, different levels of autonomy, right? So there are 6 levels of autonomy according to, the National Traffic Safety Administration here, Board Safety Administration Board here. There are 6 levels of autonomy that are categorized. Starting with level 0. Level 0 is, zero autonomy, no autonomy. The driver takes care of everything, literally what we have right now, like traditional automotive companies, right? The driver takes care of all the functions, whether it's steering, braking, acceleration. So there is nothing. Level 1 is driver assistance. You have some basic features when it comes to automated functions, right? So for example, you don't have steering, braking, and acceleration as an automated function. That's still controlled by the driver. But you have some, lane keep assist, for example, or ACC, adaptive cruise control. Some specific functions that fall under that ADAS bucket or category. Level 2 is partial automation. So what do we mean by partial? Partial is that all the vehicle has, all these safety all these critical functions of the vehicle. In other words, as you could think of, like steering, braking, acceleration, all of these are automated in the vehicle. but the driver is still engaged at all times. So in this case, the driver is required to have his or her hands on the wheel, on the steering wheel at all times, and must be alert to all the road conditions. Conditional automation, taking one step as compared to level 2. Level 3, again, it's same in terms of automated functions, right? The car is able to steer itself, brake, and accelerate based on the environmental conditions. In this case, the car is able to monitor, is as compared to level 2, right? Level 3 talks about the same automated functions, but it's not able to monitor the environment. So that's the reason why when you see the picture, you would see that level 2, the driver is basically holding its hands on the steering wheel. The reason for that is the driver needs to be alert at all times, because the driver needs to monitor the environment at all times, right? When it comes to level 3, the driver still needs to be alert at all times if any of the system fails and it needs to intervene. And that's the reason why you see the hands on the steering wheel. But in this case, the system monitors the environment, right? So the driver needs to be alert if any of the system fails. But at some times, again, depending on what the scenario is, what the situation is, but it's not required to be, attentive, like literally at all times, right? Because the system is monitoring, a part of the environment on some areas, as you would say. High automation. The vehicle is capable of performing all driving automated functions, like, again, talking about steering, braking, acceleration, right? The driver, again, they have the option to control the vehicle in this case if any of the system fails, right? And level 4 automation is a little different than level 3, because level 4 automation, in this case, the vehicle monitors the environment in a specific ODD. When we say ODD is like the operational design domain. It means that, in a specific area or region, the driver is able to, monitor the environment. So when, for any company, so an example of level 4 is Waymo's Google project. For any company, for example, Waymo or Google in this case, when the vehicle is ready to go on the public roads, they do, high level of like rigorous testing, simulating different scenarios, right? To know what's the safest option in a given scenario. And when they do that, they pick like a specific region or area before they sort of commercialize that, right? So that area or region on which they do their testing and they collect data so that they can train, their system is called ODD, operational design domain. And level 4 autonomy is that. Basically, you have that in a specific area or region, right? On which you basically have your self-driving vehicle. Level 5 is full of automation, as you can think of. That basically is, in all the areas or regions, right? So as compared to level 4, the only difference there is that, it would have all the automated functions, but in that case, it would be commercialized, right? So one of the good examples at this point, examples of level 5 vehicles are basically robotic taxis at this moment, right? For example, Nero is one of the companies that's basically doing that at this moment. Moving on. Benefits of autonomous vehicles, right? When we think about autonomous vehicles, we think about its benefits initially, at least in my mind, when I think about working on something. When I start to work on something, right, you think about pros and cons, right? And even in this case, it has its own pros and cons. For autonomous vehicles, one of the pros, let's talk about pros and then we'll go to challenges, reduce road accidents, right? Now, according to various estimates around, picking, based off the research or the articles that are there right now, around 1.2 million people, they die in road accidents every year. In India alone, if you take like 2019, there were around 1.5 approximate, 1.5 lakh road accidents related deaths. Now, with these self-driving cars that use intelligent transportation networks, they can significantly reduce these deaths by simulating millions of cases, right? And identifying options that are safest in a given scenario. The other would be, reduce pollution. Um, According to an estimate again by an environmental defense fund, and this is something that I did this research some time back when I was starting to you know get into this area or field of autonomous driving, right? So with that, you were involved in a couple of organizations or committees where you, even though apart from working on the technology itself, you also talk about its pros and cons, right? And obviously one step ahead, like how much time it's going to take to basically commercialize this technology, right? So one of the pros again is reduced pollution. So according to an estimate by Environmental Defense Fund, cars release around 333 million tons of carbon dioxide into the atmosphere annually, which is like 20% of the world's total, right? So self-driving cars that work on clean energy sources is the holy grail of transportation. Imagine a system where you have an electric car that drives around by itself for a few hundred kilometers and then goes to a charging station, fills its batteries up all the way, creating zero emissions, right? So this is like a big pro when it comes to, leveraging electric cars when it comes to self-driving technology as well. Decrease congestion. Once fully implemented, when we talk about this fully implemented fleet of self-drivings, they can significantly reduce travel time. Nowadays, if I talk myself, I, not like before, this whole pandemic and COVID, I used to spend 2 hours minimum daily in traffic, one way, in California. So with this, I think one of the big advantages of this is going to be it's going to reduce congestion. Once fully implemented, a fleet of self-driving cars, they can reduce significantly travel time by, leveraging intelligent transportation systems that companies like Lyft use for their ride-sharing business. People can be pulled into a common ride from point A to point B, and the same car then goes to point C and pick up other people and then move on. The other advantage there would be free up real estate capacity. So now, if the car is going from point A to point B and they're picking up people, carpooling and everything, other advantage there would be free up real estate capacity. Given the pressure of increased populations around the world, especially in India, real estate is of the essence, as you would agree. Right? So if cities are built around self-driving cars, then there would be drastically less need of parking spaces or parking structures, in other words, right? That just free up capacities that can be used for something else, right? It could be used to build helpful infrastructure, right? Playgrounds, parks, low-income housing, etc. Last but not the least, we have mobility. It also gives an advantage or opportunity to those who lost or never had the ability to drive. So, that's one of the advantages there, that people, who didn't have the ability to drive before, they can now leverage the self-driving car or unit technology to go from point A to point B without, relying on other people. So from there, we'll talk about a couple of challenges. Now, I just listed, a few key challenges because I know there are, so many challenges when it comes to building self-driving technology, right? But I just wanted to list out a couple here, which I feel it's like, it's top of the list in my mind. One of the challenges, the first ones would be the gap between self-driving technology level and the current regulations, right? So based on the current regulations, or even based on the current infrastructure, if you talk about India itself, right? Building a self-driving car is one, but commercializing or applying or sort of using it in India or even anywhere, even if you talk about US, it's a big challenge, right? Because there are so many federal, local, state-related regulations that you have to be compliant to before you can release your vehicle on the public roads, right? And even in this case, for self-driving vehicles, there is no such regulation at this moment because it's so new. We don't have like a standardized set of regulations yet, which is written by these organizations, in other words, right? So that's one of the biggest challenges that people need to think about. These first responders as well. For example, if there is a self-driving vehicle on the road, and if there is an accident, then how does the first responder, which could be like an ambulance or it could be like a police officer, react or approach the vehicle and gather the information from the vehicle itself, right, with no driver. So all of these regulations, they need to be in place before we start to think of, commercializing this into the world. The second one is architectures for managing complexity. As you think of, self-driving vehicle, you would imagine that it consists of so many different layers of software, right? It basically, if you look at the top, right, if you start from the top, you would have sensors, camera, lidar, radar, and then you would have perception, which sort of gathers the information from these sensors. Then you have prediction, which sort of gathers the information from perception and then predicts the movement of the objects around the vehicle, right? And then you have planning, which gathers information from prediction and then it plans its routes based on what the predicted movement is going to be for those objects around the vehicle, right? And based on that, they plan a route, like where the vehicle should be, um, and then how much brake or acceleration or steer needs to be provided to the vehicle, right? So with all of these different levels of software, it just adds a lot more complexity, right? So that is again one of the biggest challenges. Like coming to fourth point, along with this, with complexity, as the complexity increases, you have to make sure that the testing around that needs to be done rigorously, right? The testing in itself also needs to be, it also increases basically, right? Apart from doing like basic level testing, like software level testing or hardware level testing that's been done, over these years in traditional automotive companies, you also have to think about these different autonomy software layers as well, right? How do you make sure that the information that's gathered by the sensor is correct? How do you make sure that if the sensor is gathering correct information, that's been correctly fed to planning or prediction? Or if you get a correct route, how do you make sure that the controls part of it, which is like the last part, how do you make sure that the controls, even though it's getting the correct route from planning, you make sure that it's feeding the correct amount of torque to the actuator, right? In the case of steering or braking or acceleration, in any of these cases, right? So you need to do all these different levels of testing, and this is where verification and validation becomes a big challenge. The last but not the least is safety, right? Now safety has its own challenges. If you talk about safety, I usually think of safety into two buckets when it comes to challenges, right? One is general challenges, right? When we talked about these regulations. So safety and compliance is one of the challenges. Like how do we make sure that the infrastructure that we have right now, it supports self-driving vehicles, right? That's one bucket. The other bucket is technical challenges, right? Like all the sensors that we are using in the vehicle, the control systems that we have in the vehicle, right? How do you make sure that the sensors, they they behave as it's supposed to? Like you get intended behavior from these sensors, right? How do you train your neural networks, for example, right? You basically have to train the data. You basically have to collect data and then train the system to gather information before you can deploy your self-driving vehicle. How do you make sure that that's correct, right? So all these technical challenges for safety, it's huge. Right now, I don't think there's anything which sort of lays out like a process. So this is how you can safely test your neural networks, safely test your autonomy stack, in other words, right? And that's the reason why it's a challenge, because it's unknown. And people have started to think about it. They've started to work on different standards. For example, IEEE and SAE, they have been started to work on different papers and standards. They're starting to lay out best practices when it comes to safety testing, right? So people can start from there as a basis. But again, it's a big challenge, right? To accomplish safety in the end. Moving on to, now we talked about high level, different levels of autonomy, its benefits, its challenges. Let's dig into safety. Functional safety. Now, when it comes to AV, autonomous vehicle safety, right? It's not just functional safety. And I'm going to go back to the definition of functional safety once, I'll just, talk about this image that I have there on the screen. It's not about just functional safety. That is ISO 26262 is a standard for functional safety. We also have to talk about different levels of safety, different pillars of safety. especially for AV, right? Functional safety, the definition of functional safety, right? It only talks about electronic and electrical systems malfunctioning behavior. In other words, you have a system or an ECU, electronic control unit, right, in the vehicle, and there are so many ECUs in the vehicle now. If any of the ECU fails, for example, or it provides invalid input, or just picking an example of a control system, right? Pick an example of um, brake control ECU, for example, right? So functional safety only applies to electrical and electronic components, and it applies in a sense that it basically makes sure that if any of that system fails, in this case brake ECU, right, or if it provides invalid output to the actuator, in this case brake torque to the actuator, then how what the vehicle response or behavior is going to be, in other words, right? So you think about different scenarios when it comes to applying functional safety. Take this picture, for example, right? In this case, there are so many, as we talked about different levels of software, right? Functional safety applies all over, right? Because it specifically applies to if there is a malfunctioning behavior in any of the systems, right? And there are so many systems. System can be, the definition of system can be, for example, brake ECU as one system, uh, propulsion ECU is another system, for steering, it's another system. So that's how you can define our different systems in the vehicle, right? And if you think about going by this definition, you can think that that's going to be so many systems in the vehicle, right? For each system, you do the analysis, safety analysis, right? And you determine that what if this system fails, what the impact is going to be, the vehicle level impact is going to be of that failure, right? If the brake ECU sends invalid brake torque, right? You can imagine, in a specific scenario, the severity of that failure is going to be high, right? And you think about different, you think about different, how do I say that? Parameters in this case, right? So severity is one. You think about how severe that failure is going to be, right? You also think about how probable that failure is going to be, like the probability, like the occurrence of that failure. It all depends on where you are in the environment, right? If you're reaching an intersection, for example, approaching an intersection, and if there is an unintended acceleration of the vehicle, right? If you're driving at, I don't know, 5 to 10 miles per hour speed, and you're approaching an intersection and there is an unintended acceleration, then based on that specific situation or scenario, you rate your severity, how severe that failure is, right? For that severe, you sort of think about different situations or scenarios. What if there's someone crossing the intersection, right? And if there's unintended acceleration, then you can hit that person, right? So it's not always about the passengers inside the vehicle, it's also about the passengers outside the vehicle, right? When it comes to determining the severity. Uh, the other parameter that you think about how probable it is, right? So you think about the situation, right? And it's highly probable, right, that you're approaching an intersection, like the situation, how probable that situation is or scenario is. That there is a red light, you're approaching an intersection, and there is someone crossing the road. That scenario, it's possible, right? It's highly possible. And then the other one, you think about how controllable the vehicle is, right? And if that happens, how controllable that vehicle is, right? And that varies for different levels of autonomy. Um, for level 2 or 3, you can imagine that there is a safety driver, and you can imagine that if there is an unintended acceleration, then there is a warning to the driver, and the driver is ready to take over because the driver is alert at all times, right? So that is maybe controllable if the driver is ready to take over, right? For level 5 systems, for example, that's fully automated, it completely depends on the system, right? How safe the system is, right? That it's able to control that specific scenario. So it varies for different levels of autonomy. Now, because functional safety only applies to, going back to the picture that you see at the top there, functional safety because only applies to, malfunctioning behavior of systems. It does not apply to outside of malfunctioning behavior. For example, if there is a sensor, right, and if the sensor is working fine, there is no malfunctioning behavior, but it's still giving you unintended, behavior, right? How do you react to it, right? And this is where it adds complexity, Because for traditional automotive companies, they have been using this functional safety standard for like so many years now, right? And it was okay to use because there is a driver in the vehicle, and the driver, in most of these scenarios, the driver is able to control the vehicle, right? But when there is no driver, how do you define controllability, right, of the vehicle? How do you define scenarios or situations where the system is working fine, but because of some external factors or environments or road conditions or weather conditions like rain, snow, you know, your sensor is not working fine, right? So that's the reason it adds more complexity to the system, and it basically requires more testing to the overall system. Going to the definition of functional safety, I also wanted to explain it by chain of implications so that you understand um, how it basically goes from one step to the other, and how do we determine you know um, like the malfunctioning behavior of something could lead to something, in other words, right? So functional safety definition, thinking of it as in chain of implications, right? Let's say there is a malfunctioning behavior of E component, picking anything in the brake ECU again, going back to the same example. The next thing you do is, once you have identified what the malfunctioning behavior could be of that component of that system, you define hazard at the top level or the vehicle level, or how the vehicle is going to behave if this happens, right? Or if this failure occurs, right? Then you define how the vehicle is going to be, the vehicle is going to behave. The next step, you find out what is the risk of that harm, right? Let's say there is unintended acceleration or unintended braking or hard braking, right? Because of that malfunction in the system, you define what the risk is going to be. And the risk again depends on these three parameters that I talked before, right? It depends on the risk of harm to people inside the vehicle and to people outside, around the vehicle and the environment. So it again depends on three parameters that I talked about, like the severity of the failure, controllability, and it also depends on probability, right? Occurrence of that failure. Based on these three parameters, you define your risk level, right? Again, if you go back to the standard, functional safety standard, it exactly tells you based on these three parameters, if you pick XYZ for these three parameters, this is what your risk level is going to be. And based on that risk level, you have to define safety mechanisms or features to reduce that risk. Now, that safety mechanisms or features, it's a combination of both hardware, software, testing, vehicle level testing, different levels of testing, basically, right? Vehicle level testing, software testing, hardware testing, system level testing. It's a bunch of, like, a lot of things, right? It's more like a process. So based on that risk level, you define a process around that risk level to reduce that specific failure or malfunction. And a quick example of that would be another system, for example, electronic throttle control system. In this case, you find out a failure for that system. What unintended situation could happen? In this case, let's say unintended acceleration. How likely is the hazard to happen? How the severity of that failure, how harmful it is, in other words, and how controllable it is, right? And then based on that, you define risk level, and then you try and sort of reduce that risk by adding safety measures, safety mechanisms to the system, to both hardware and software. Quick example, and this is something that I was actually interested to hear your thoughts in the chat window. So feel free to tell me what you think of it. So this is just a quick example of electronic throttle control system. The reason I wanted to pick this is because I wanted to give you guys a sense of, when we talk about different malfunctions, right, or different failures of that system, what are some of the examples of those failures? This is just a very basic block diagram of electronic throttle system. As you would see one input, you have accelerator pedal sensor, so the driver presses the pedal and you get an analog signal to the system, to the ECU. You have another input as vehicle speed. You can sort of define your what the output, based on the information that you gather from vehicle speed and other inputs. You can define your safety envelope, right? Like as a function of vehicle speed or vehicle velocity. And obviously, you have other other vehicle systems inputs that you get. The communication I've mentioned there is CAN, so controller area network. CAN is one of the most commonly used communication protocol in the automotive industry, as this is reliable, and when it comes to safety, it's actually reliable when it comes to safety. And the output there you would think of as talk request, you know, and the other one is module status. Module status would be, let's say, if there is any internal failure for this ECU, then it needs to be communicated to other, systems around it, so that they can obviously take whatever action it needs to be, it needs to take based on the fault status of the specific ECU. So, based on this ECU, I'm happy to actually look at the chat, because I'm looking at the chat as well. What different failure modes you can think of, that could lead to maybe unintended torque request, invalid torque request, or no torque request at all, or delayed torque request, right? Because if you're expecting to, if you're expecting, let's say, at some frequency, right, it needs to be sent at some frequency, x hertz, for example, right? And if it's not sent at that specific frequency, and if it is delayed, what is the impact of that delay to the overall system, right? So, couple of failure modes. Let's see. So one of the failure modes there would be that the signal is out of range. Now, the driver presses the pedal, right? Accelerator pedal sensor. You get the analog signal. You read that analog signal, because based on that, you decide that there is a driver intervention. Let's pick level 3 autonomy, just to pick an example, right? For level 3 autonomy, just to go back to the previous slides of different levels of autonomy, all the critical functions like steering, braking, and acceleration, they're all automated, right? And the driver can just sit back and relax, but obviously be attentive, or sort of, is able to intervene, when there is any failure or there's any warning to the driver on the dashboard. But in this case, for example, if there is a failure or a fault, or if the driver monitors the environment and sees that, okay, I need to, either accelerate, I need to stop, or brake, it needs to press the pedal. So if there is a pedal press, you get the input to the ECU and you get the notification that, okay, driver has pressed the pedal. This is an indication of, disengagement. That means we need to get out of autonomy, right? And based on that information, you basically, based on that, you set your torque request, right? Now, let's say, because you are dependent on that pedal input from the driver, and if you don't get that pedal input from the driver, if there is a fault in the sensor itself, right? Or if there is a signal, for example, this analog signal that you're reading, based on how do you know that there is a driver request, right? Because you can relate it to a specific voltage. For example, in this case, for an analog signal, let's say if the signal is out of range, right? Meaning that the voltage which says that, okay, the driver is pressing the pedal, it's not giving you the correct information, right? It's basically is out of the range, meaning that the driver is pressing the pedal, but you're not getting that information, right? In other words, you determine your torque request as a function of vehicle velocity, for example, to develop your safety net, right? And if you don't get that vehicle information or vehicle speed information, how do you determine that, output? That's one of the other failure modes. The other failure mode would be invalid torque request, right? Again, I mean, if you're getting invalid input, that can lead to invalid output, right? So if you're getting invalid input from here, signal out of range, or invalid vehicle speed from as an input, that can lead to invalid torque request, which obviously can lead to unintended acceleration in this case, right? So you think about these are like very basic, very high level failure modes, that you basically, at least for me, I start to think of any ECU picking these specific failure modes, basic failure modes. And from there, you add on top of these failure modes, like a lot more failure modes, right? That goes into the hardware area, that goes completely into the software side, for the microcontroller itself, right? You think about operating system, the OS that you're using. You think about base level, like the low level embedded layer failures as well, right? Register specific failures, memory failures, they have so many different failures that you can think of, and you need to address, and you need to add a mitigation, or you think of a way to know if that failure happens, then how do you react to that failure, right? In this specific example, we have talked about failure modes, right? And we know that, it could lead to a bunch of these failures. We could also have delayed fault status, right? How do you address these failures? What do you do to address these failures? Some examples there would be, this is the same, again, diagram. One of the things that you can do is you can add additional sensor, right? So let's say if sensor one is giving you invalid input, then you don't have another way to verify that information, right? By adding additional sensor, redundant sensor, you can verify your information with another sensor, and you can be sure that, okay, this is a failure or this is not a failure, right? Um, in this case, for example, the way the logic works in the ECU is that you get analog signal information of voltages from these two inputs. And then, let's say there is, let's say going back, let's say there is a specific ratio that needs to be maintained between these two sensor inputs. Let's say 1:2 or 1:3 or 2:1, whatever, right? And if it's not within that specific ratio, then you know that there is something wrong, right? So you just add additional sensor just to be sure that, okay, if one sensor fails, either it depends on how you define your architecture. Either you depend on the ratio, or you can just add a completely redundant sensor. In other words, that if one sensor fails, you have a backup sensor that you can fall back to, right? So you can ignore the first sensor because there is a failure, but you can fall back to sensor two and you can get that information instead of going to instead of taking a drastic action because of sensor failure. You can not take that and you can rely on another sensor and continue driving basically. And some other mechanisms that you can add at the output, on the output side, basically, right? You can compare inputs from these two sensors, as I just talked about, to know if one of the sensor fails, then you know that there is a fallback, right? Fallback mechanism. You check for message corruption on the output. So the talk request side, right? So as you're getting that information over CAN, the communication protocol, you can basically check for message corruption, right, over that bus. So you can check that over that, CAN, the communication bus, if the message got corrupted, if the message was delayed, there's a timeout, right? In other words, or if the message was dropped in between and you didn't get that information, right? So you can add different mechanisms to sort of make sure that you're getting correct information, you're getting information on time. And you can add different mechanisms as well to sort of add like a plausibility check, in this case, to a sensor, right? Plausibility is, that you can add a different source of information. You can compare it with different source of information. You can also monitor feedback from the vehicle, right? You can also gather additional, for example, from here, other vehicle systems. You can also, based on vehicle dynamics, right? You can also gather some steering rate, for example, from the vehicle, and you can compare it with additional other inputs that you're getting, and you can see if there's something wrong, right? So you can compare the torque, for example, the steering torque that you're requesting, based on what you're requesting and based on what you're getting from the vehicle, right? If it's making sense. And if not, if there is a big delta, huge delta, then obviously you know that there is something wrong somewhere. So based on that, you basically go about defining your failure modes and defining how do you approach making sure that you have addressed those failure modes in the architecture. So this was functional safety. Functional safety is very specific to identifying different malfunctioning behaviors of the system, right, as I talked before. But if you take one step up, right, for AVs specifically, autonomous vehicles, functional safety is not enough, right? Because you need to, because of this added complexity for autonomy stack, you need to talk about different limitations, right? Like what if the sensor, again, going back to the previous example, what if there is a bright sunlight, right? What if there is a bright sunlight on the camera lens? The camera is working fine. There is no failure in the sensor itself, but because there is a bright sunlight, falling onto the lens of the camera, it's not able to. It's basically giving you unintended output, right? So it's outside of its limitations. Another example would be, weather condition. For example, if you're driving in rain, and the camera or any other sensor is not able to gather information again because there is no failure, right? But because of environmental conditions or external conditions or limitations, the sensors or any other autonomy stack is not able to, give you the correct output or what's intended, right? How do you make sure that you've captured all of these cases or scenarios? So that's why we say that, SOTIF. So SOTIF is another standard. I didn't want to mention SOTIF there because there are so many standards. But if you just look at this diagram at the top right, SOTIF, safety of the intended functionality, is a standard which captures, all of these extra on top of functional safety, scenarios or different, um, use cases, corner cases, for example, based on which you can simulate or, simulate different scenarios or use cases, and you can test your vehicle, right? Um, Now the question arises that, how do you make sure that you have captured all of these scenarios, right? Because it's you would have known scenarios, you would have unknown scenarios, right, as well. You can obviously reduce the section when you talk about known scenarios by, adding a more simulation cases, simulating more scenarios, or adding additional test vectors, um, testing more on the road, or testing more on the vehicle versus on, on the bench, for example, like a test bench. So you can do that, and you can reduce that sort of known section, and you can add mitigation to it. But when it comes to unknown scenarios, again, it's another section, right? How do you do that? And I think this is where the complexity or the challenge falls in, right? Um, you can try your best to sort of run millions and hundreds of, use cases or corner cases based on, your judgment, based on the standards that are there already, SAE and IEEE, or even the safety organizations that they're working on. Um, but there's always, you can do your best from your side, but you can't be sure that you have covered 100% of these cases, right? So this is where that complexity and challenge falls into. Like, how do you get to that 100%? How do you measure safety, right? How do you make sure that you've reached 100% safety? And the final one, as you look at this diagram again, is the last pillar, other pillars of safety apart from functional safety and SOTIF, right, where it talks about different limitations of these sensors or technology limitations. It talks about different areas or aspects as well, right? So cybersecurity is one of the bigger challenges as well. When you talk about these AVs, right? Not at the moment, but moving forward, when you start to commercialize it, you can think of V2X communication, right? Vehicle to vehicle communication, or vehicle to operator communication, right? Backend operator communication, right? And cybersecurity falls basically under that section or area, right? So that is again one of the challenges and the areas that it needs to be addressed, and it needs to be thought about. Regulatory requirements, we already talked about the challenges, and how do we see that the current infrastructure does not, support the development of AVs. So what needs to be done? And again, this is like unknown because we don't have, a set of principles or guidelines which tells us, what needs to be done to support, in terms of, making sure that the AV supports this set of guidelines, for example, for the development of AVs. And then last but not the least, again, I just picked, key pillars of safety here: comprehensive safety simulation analysis. So this is again going back to the previous two examples. All of this is interlinked, basically, right? That you think of different like simulation corner cases or use cases that you have to run to sort of get to a point where you can be confident enough that your vehicle is safe enough to be driven on public roads, right? Because it's not just the company, it's also about different organizations outside or boards that needs proof from different companies in the form of a test data, in the form of a safety report, for example, that needs to show that you have done enough, right, from your end to show that the vehicle is safe enough to be driven on public roads. So there is a process to it. It's not just functional safety, or it's not just SOTIF, it's not just cybersecurity or other pillars, it's a combination of all of this. And some of it is there already, like functional safety, ISO 26262, there is a standard. Even for SOTIF, there is a standard, but the application of that standard, it's not um, the application of the standard, like all of these companies right now, some of the companies are applying that standards, but some not, right? So it's not commercialized in that sense. With that, we'll go into Q&A. So happy to take any questions about the background, course, safety specific questions. So yeah. Back to Mehak, I guess, or
Hi, that was very informative session, I must say, and that That was very, very informative. That the chain where way you explained it really went very well. So,
Yeah, I hope so because there's so much to it. It's really difficult to you know gather all the information into those 2 or 3 slides because functional safety in itself, it's a standard of 12 parts, right? And each and
yeah,
every part, it has like hundreds of pages. So yeah, so it's a process basically, as I said, right? So you start from the basic and then you add on top of it.
I think that was enough to bring interest. And like I, for personally, mine had never heard about anything in this detail. But now, after
Yeah.
hearing all this, I am really interested to learn it more. Okay, so moving towards Q&A. So you have answered most of the questions during the session itself. But we have some questions from the registration form we put on, and I'd like to bring up them if you're ready.
Yeah, go ahead.
So the first question is, which careers are offered in the branch of electronics?
Your voice is breaking. Can you repeat that?
Which careers are offered in the branch of electronics?
Um, a lot of careers. I picked control systems as my major because I felt that it was so I didn't like coding that much, and I wanted to you know pick something which was not coding, to be honest. And I found control systems a practical mix of both hands-on courses, like working with microcontrollers and control systems itself, and then also mathematics because I've always had like a bent towards mathematics. So I always like that control system. But I think apart from control systems, there are other courses that can sort of help you get into the same line if you want to, like embedded systems, right? Because safety again applies to all, and even for electronics, it applies to all, right? So you
Yes,
would have embedded systems, you would have signal processing, you would have power systems, network and communication, um, you know, um, power and energy, in other words, right? So yeah, it's like, a big list of courses that you can, because electronics, I feel it's like a very generic term, right? And underneath, if you look, it has like a big list of courses that you can apply to, or if you can be interested into. So
yeah. Okay. So next question is, other than safety engineering, what are the other departments that play an important role in the robotics industry?
apart from safety, I think a lot of areas, to be honest. Because as per my role, I work with, because safety is such area where you have to work with different teams, right? You have to make sure that each and every system is safe, right? So you have to apply the safety process to all of these systems, right? And if you think about different areas where you can work, it starts from all the way from the top, right? If you think about AV, it could be, if you're interested in software, for example, if you want to go software, or if you have coding experience, it could be anywhere from, sensor to perception, prediction, all the different levels that I explained before, to planning, controls. If you have, because I've had MathWorks or Simulink and MATLAB experience, so that's the reason why I did software development before and control systems. So if you have that specific experience and you don't want to go into hands-on coding, you can sort of apply to control systems more. But if you want to more challenge, and if you like coding, then obviously there are so many different levels of software that you can apply to. Um, apart from that, apart from safety and apart from the autonomy stack as well, there are different teams in the company at Lyft, for example, that I can talk about, like systems, for example, system engineering. It's a complete new team that is on V&V activities like verification and validation. So you're more interested into testing aspect, right? Or if you're more interested into requirements, sort of writing the requirements for the system or verifying the requirements for the system, um, or for safety, non-safety, um, testing it on the vehicle, testing it, on the bench, like a test bench. So that's what systems team is responsible for, right?
Okay.
Apart from that, you have a bunch on the hardware side as well. So this was all software, right? And systems is a combination of both at the system level, basically. It's a combination of both hardware and software, right? But apart from that, you would have a lot more on the hardware side as well, right? If you have around, right, then you have mechanical teams. If you have, a very core hardware background where you have to work on designing boards, sensor boards, then you have specific hardware development teams that you can be involved with. So it's huge, like, it could be anything. And electronics, I feel like it's so generic that it literally applies to a lot of these areas, and a lot of these teams. So,
Okay, so we have one question from Pranav Tushar in YouTube chat. What would be the roadmap to become a successful control system engineer?
um, I guess it'll start from uh, at least I can pick my example, right? I guess what I did because I wanted to get into controls again because of a practical mix of mathematics and hands-on courses like microcontrols and all of that. Um, I wanted to do a master's there, picked specific universities where I knew that they have good controls courses to begin with, and even if it's India or if it's US, irrespective, right? I personally wanted to go to the US, so that is one. But I think irrespective, if you want to study in India or if you can start by, or at least that's what I did. I started by browsing through universities that have like best controls courses, right, in the world. And then you start and talk to I started personally talking to the professors there. So you obviously get a good sense of, how can they help and what are their areas, what sort of projects do they provide and offer at the universities or different courses in the university, right? From there, you had, once you pick that course, you had like so many hands-on projects. So I think one of the other things that you can do once you get into the university is you can try and get involved into different these companies or organizations or projects, right? Because that way you'll get more hands-on experience into, all of these control systems, right? Theoretical is one, but if you work on these projects and if you work with professors, so there was another advantage there that some of these professors, I wouldn't say all of them, but some of the professors, they were working with these automotive companies in Michigan, right? So they had this practical experience, so they knew what's there in the outside world and what can help us, gain, and we can sort of go back and provide our insight, right, when we go and work for a company. So that also helped, right? Working with the professors personally and doing some research, working on any project that you can volunteer for example. It's not always open for, you'll probably have to volunteer a lot more to these projects. um, and then from there, I think when it comes to picking a job, for me, because Michigan was the reason I picked University of Michigan because of the area. One of the reasons was the area itself, right? Because of the automotive industry in Michigan. And then once you look for jobs, and once you're looking for a job in automotive industry, um, you can obviously pick your job, as per your interest there, control systems, for example, right? So.
Okay, so we have next question from Abhay Singh. According to you, as a safety engineer, what the company should spend more money on? Cyber shield of the AV or general security measures like road accidents prevention measures or equipment?
I think it's a mix of both, I would say, because the reason I say it's a mix of both, because it's not just safety, it's safety and compliance, right? Some of these
Yeah.
areas fall under safety, but some of these areas, they fall under compliance, where you have to show to, you know, to the agency or to the outside. I don't know how it is in India, but in the US, you have to show and you have to publish a report on a quarterly basis showing how many accidents you had or how many disengagements you reported, right? How many times did the driver intervene or how many times did the system intervene, right? So all of the metrics you have to provide to them. So I think it's a combination of both. It sort of falls under different pillars. It falls under safety and compliance. So when you talk about cybersecurity or safety cell that's working on these different measures, that's engineering effort. But if you talk about these road accidents prevention or sort of the metrics that you provide along with that, it falls under compliance reporting, for example. So, but I would say compliance reporting falls, slightly if you compare these two. Compliance reporting falls, higher because if you don't provide, you won't be able to drive onto public roads. So if you don't provide that, and then you won't be able to drive onto public roads, and this is something that's like a blocker for the whole organization, right? You make sure that you do that, you provide that metric, so you can sort of start to test your vehicle on the public roads. Because if you don't do that, you can't even test your vehicle on the public roads. So maybe slightly higher on that list, I would say. Then.
Okay, I guess that was our last question. And thank you so much, Palak, for being here. This was really very amazing. This is an amazing session, and all that coming from your side was very informative. Thank you so much.
No worries. Well, thank you for having me. It was great, talking. And yep, thank you again. You all have a good night.
Good day.
Take care. Bye.
Bye.